requires cars entering a freeway to stop for a certain period of time before joining the traffic flow. The theory is that ramp metering controls the number of cars on the freeway and the number of cars accessing the freeway, resulting in a freer flow of cars, which ultimately results in faster travel times. To test whether ramp metering is effective in reducing travel times, engineering and mathematics in Minneapolis, Minnesota conducted an experiment in which a section of the freeway had ramp meters installed on the on-ramps. The response variable for the study was the speed of the vehicles. A random sample of 15 cars on the highway for a Monday at 7 p.m. with the ramp meters on, and a second random sample of 15 cars on a different Monday at 6 p.m. with the meters off, resulted in the following speeds. Okay, so are we clear? The average speed at 6 p.m. on this particular freeway on a Monday night, right? That's population 1. The average speed of this freeway at 6 p.m. on a Monday night with no lights, no ramp meter thing. That's one population. The other population is the same freeway, the same time, the same day, but with the lights on. So the only thing that has changed is whether or not the lights are on or off. And now we're going to see if the average speed of the cars is different. All right, so let's start off by writing down our hypothesis tests. Okay, so what's our null hypothesis? They equal each other, right? That part should be really easy here. It's always the same. Null hypothesis is that the mean of both populations is in fact exactly the same. That's our first step always. Step 1, null hypothesis is that mu of 1 is equal to mu of 2. The meters, the lights make no difference. The population of the average speed on the freeway is going to be the same whether you have the lights on or off. Right? Who thinks that's the case? That those little things make no difference? Huh? You guys all think it does make a difference? The freeway is better? The speeds are faster when those lights are on?
It's always slow no matter what.
Okay, so you don't think it makes a difference then?
Or if life sucks.
Okay. Well, does it suck less? I'm not saying it's going to be great speeds. The argument is that it's better, right? So instead of doing 7 miles an hour, you get to do 10 miles an hour. It's a little bit better.
Right.
What's our null hypothesis? That they're equal. So what's our alternative hypothesis?
Not equal.
Maybe not equal to, but you know, it's guided by the word problem here. Let's see what it says. Does it give us a hint as to what they think? To test whether the ramp metering is effective in reducing travel times. They're betting that it's less, that it's going to help, right? So we need to decide which one is which, right? For your sake of your own notation. Is this the one with the meter on, or is this the one with the meter on? So let's pop number one be meter on. Meter on. And so pop number 2 is meter off. So we're saying that the mean speeds are going to be better when the meter is on. So our alternative hypothesis is this, that the typical speed, the mean speed of vehicles on this freeway is going to be better when the meter is on, right, when you're stopping people. All right, so now that we have our hypothesis, now we got to go treat our data. So in this case, we got these 2 sets of data. So what are we going to have to do? List 1, list 2, 1 variable stats on them. You got them? Here, let me copy them on here. 28, 38. Okay, so we have our sample 1, sample 2. So this is pop number 1, meter on. And this is pop number 2, meter off. And n sub 1 is 1, 2, 3, 1, 2, 3, 4, 5, 15 values. And n sub 2 is also 15 values. And now we put them into our calculator and we'll get this and this. Did you guys do it already? Okay, so we have our two samples that are given. We found everything we need from our samples. So now we want to see if perhaps it shows that. Well, the samples tend to kind of guide us that way. Look, the average speed, the mean speed with the meter on was 40 miles an hour, whereas with the meter off, it was 34. So maybe it's helping a little bit. Well, someone might say, well, that's just a fluke. It's just luck. You just kind of happen to get 15 randomly selected cars in a particular day if you go on a different selection of cars. So we need to judge, well, let's find out the probability that this is just luck. If this is in fact true, that there is no difference, what's the likelihood of getting two different results like this? Okay, so the third thing we do is write down our test statistic, which was T naught equals to x bar 1 minus x bar 2 minus mu 1 minus mu 2 all over s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And we want the square root of that whole thing. By the way, are we guaranteed that this is going to work? What do we need to make sure that this is going to work? Our sample size has to be greater than 30 or it has to come from normal distribution. Do we know, does it say in the word problem to assume that this comes from a normal distribution? Sometimes it'll say in the word problem, assume that the data, so you don't have to worry about it. Let's see. Ramp metering, freeway stop, joint flow, theory, control, accident resulting, ultimately faster. Minneapolis conducted experiment 15 years, ramp, sponsor a study. Monday ramp meter on, finding speeds. It doesn't say anything about that. So what do we do if they don't specifically tell us that this comes from a normal distribution? We have to do a normality plot, right? So we already have all our data onto list 1 and list 2. So go over to the second shift stat plot, do a normality plot, list 1, make sure that all those little dots look like they're kind of in a straight line. That'll confirm for us that this comes from a population that's approximately normally distributed. Same thing for list 2, do a normality plot on that one. We'd also want to do a box plot to determine if there is any outliers. But just looking at those numbers, there wasn't really any number that really sticks out as being very far away from the others. I really doubt that this has that. But you can do a box plot with your calculator and see if there's any number that kind of sticks out. Confirms that these are approximately coming from normal populations. So now, do we have everything we need? Remember that for us, under our null hypothesis, we're assuming that's equal to 0. So we have that, we have that, we have that, we have everything we need, so we can find our t-value. T sub naught is equal to 40.6667 minus 34.5333 divided by, and we have 10.0404 squared all over n sub 1, which was equal to 15, plus 9.5608 squared all over 15, and then it's the giant square root of all that. So let's figure out what that is. T naught equals to 1.7134. Okay, so that's our standard t-value. This equation automatically gives it to us in our standard t-value. This will be the number that traps the area in that standard t-distribution, which is proportionally equivalent to the area we want. So we can find the likelihood of getting such a result under the null hypothesis. So we can graph this. So this is the standard t-distribution. With how many degrees of freedom? Degrees of freedom equal to 14. And the mean of this distribution, mu sub x bar, oh no, I'm sorry. The distribution is equal to 0. And we have a value of 1.7134, which is going to be there. We want that right there. We want that area. The likelihood we would get that result or something more extreme. So that's our p-value. p-value equals to normal TCDF from 1.7134 up to positive infinity with 14 degrees of freedom. Okay, and then our final conclusion is going to be what? Are we going to reject it or fail to reject it? What do you need to know in order to decide whether to reject it or not reject it?
Alpha.
Alpha. It'll be given to you. And what did they say here? Use
10.
10, right? So use alpha equal to 10.
So we don't reject it?
When this is small is when we reject it. When the probability that's true, when the likelihood is very, very small that we would get such an extremely rare result, that's when we reject the null hypothesis. So because the p-value is equal to 0.05434, which is smaller than alpha, is smaller than 0.10 equal to alpha. The likelihood is too small as relative to that. Therefore, we reject the null hypothesis. Reject the null hypothesis in favor of the alternative. Questions? No? No? Okay. Not too terrible, right? Sort of, kind of? Maybe? Alright, it's terrible. Alright. 2 down, 2 to go. Yeah, go ahead.
If they didn't label the standard T distribution, would be mean 1 minus mean 2
Where are you talking about?
on the graph.
It's a standard t distribution. So these are little t values,
Oh, it's
right? They come after we've already like standardized it. This equation already gives me the standard t distribution.
so it would be T.
Yeah, these are little t values here. Of one of which is this one. So that's why that belongs there. It's the t value that results under the null hypothesis. That's why it's got this little sub O there. So it's a little value on there, which is a t value.